Hello, Assalamu alaikum. Good morning, class. Today we'll have another lecture, online lecture of the chemical reaction engineering. So the lecture outline of today's consists of performance equation of ideal plug flow reactor, which we have already derived in the physical class, and then we will see the examples using the application of ideal plug flow reactor, and then solve the problems from chapter number 5 utilizing the concepts we have covered so far from chapter number 5. So here you can see the comparison between the plug flow reactor and the mixed flow reactor. Both of the performance equation of both the reactors, whether it's mixed flow or plug flow, we have derived in the class. And you can see if we start from the mixed flow reactor design, after applying the mass balance across the reactor, we get this uh, which is which is you can see V by Fa naught is equal to tau by Ca naught is equal to Xa over minus Ra. And for the plug flow reactor is the same, but only difference is that we have to solve the integration uh, between the dxa and minus Ra, and tau over Ca naught left hand side is the same, so we have to perform the integration here. And the difference in the graphical method is that for the mixed flow reactor we have area above and below of the line, the curve, and on the plug flow reactor we have just to calculate the area below the curve. So this shows that the here it is already shown that the mixed flow reactor, for the same conversion we need higher amount of area, and that ultimately corresponds to the volume. And for the plug flow reactor we have lower area, and that means we have lower volume for the same conversion. So for a given conversion, let's say 80% conversion, mixed flow reactor areas, or volume will be higher as compared to the plug flow reactor for the same given chemical reaction. So we just summarize the performance equations of the reactors which have derived so far. The performance equations can be written either in terms of concentration or conversions. Like you can write the performance equation, the right hand side, in terms of concentration or conversion. For systems of changing density, it is more convenient to use the conversions. However, there is no particular preferences for the constant density systems. So if you are given the concentration and you have to find the conversion, so you can take the conversion on the left hand side and write the expression in the form of concentration. And if you are given in the statement the conversion and you need to find the concentration, so you can take the concentration of the left hand side and the conversion on the right hand side and solve the answer for the required concentration for the given conversion. So whatever it's the form, the performance equation interrelate the rate of the reaction, the extent of the reaction, and the reactor volume and the feed rate. So if any one of these quantities is unknown, it can be found from the other three. So there are almost four variables. What are these? Rate of the reaction, the extent of the reaction, and the extent of reaction means conversion, Xa, and reactor volume and feed rate. That will be the molar flow rate or volumetric flow rate, Fa naught or V naught. And if any of the three quantities are uh, uh, like known, and you have to find the fourth one, so we can find the fourth value by using the this performance equation. So figure 5.6 displays this performance equation and shows that the space time needed for any particular duty can always be found by the numerical or graphical integration. So we can solve these integrations to calculate the space time. However, for certain simple kinetics, from analytical integration is possible and convenient. So all the performance equations for different orders and different like values of the chemical reaction, reversible, irreversible, density, varying density, or constant density, we can solve the integration by simply numerical methods also, which are more easily. And so you don't need to solve the detailed integration. Just you put the values in the final formula and you can calculate the answers. So to do this, insert the kinetic expression for RA in equation 17 and integrate some of the simpler integrated forms of plug flow are as follows. This we are just talking about the plug flow reactors or also batch reactors, because batch and plug have integration inside them, but mixed flow reactor have no integration in its performance equation. So zero order homogeneous reaction at any constant EA. So here you can see for zero order reaction, this is for the plug flow, the equation becomes K tau is equal to K Ca V over Fa naught. That becomes equal to Ca naught Xa. So you can directly use this equation to solve. If you have zero order, you don't need to do any integration. It's already solved integrated form. So for first order irreversible reaction, A goes to product at any EA. You can see that the equation becomes K tau minus 1 plus EA ln 1 minus XA and minus EA XA. So if you have given that we have first order reaction and you have the uh, varying density case, so you can find the tau value if you know the conversion and K value from this equation. So and for the first order reversible reaction, like this is the first order but reversible, like forward and backward reaction, and Cr naught by Cr naught is equal to m. The kinetics approached or fitted by minus Ra K1 A minus K2 Cr. The observed equilibrium conversion XAE constant EA. We end up with this expression. You can see here the equation 22. K1 tau is equal to m plus r x a e m plus r minus 1 plus ea xae ln 1 minus xae minus eaxa. This is for the reversible first order expression. The solved integration by the numerical method, which you can use to calculate the any unknown value after like for example, if you know m value, xae value, r value, k value, so you can calculate the tau value, which is the space time. For second order irreversible reaction, we come up with this equation. It's more complex. You don't need to derive this expression. Just utilize the final expression in the given problems, which will solve directly by using these equations. So if we have second order irreversible reaction and with equimolar feed or two-way goes to products at any EA, we end up with this expression Ca naught K tau is equal to 2 EA volume expansion factor 1 plus EA ln 1 minus XA EA square XA plus EA plus 1 square XA over 1 minus XA. So you can calculate any unknown value by putting all these values by this directly utilizing this equation. So this is the last slide before we go on to the solving the examples and problems regarding the application of performance equation of the plug flow reactor. These are the summarizing points from the theoretical concepts we have covered so far. Now, where the density is constant, of course, you know that we will put the volume expansion factor is equal to 0 to obtain the simplified performance equation. By comparing the batch expressions of chapter 3 with these plug flow expressions, we find that for systems of constant density, constant volume batch and constant density plug flow, the performance equations are identical. Tau for plug flow is equivalent to T for the batch reactor. So, and the equations can be used interchangeably. So here we say that the performance equation of the batch reactor and the plug flow reactor are similar, because in the both equations we have to solve the integration. Just the difference is that in the batch reactor we use the time, normal time, and in the flow reactor, the plug flow reactor, we use the space time, that is tau. And the second point is that for the system of changing density, there is no direct correspondence with the batch and the plug flow equations, and the correct equation must be used for the each particular situation. In this case, the performance equations cannot be used interchangeably. So when we have constant density system, we can use the same expression for the batch reactor and the plug flow reactor. But for varying density, we need to develop separate equations for each case. Like we have different orders: zero order, first order, second order. Then we have reversible reactions, irreversible reactions, and we will develop the expressions accordingly to the reaction conditions. So this is the first example. In fact, this is the uh, first example in terms of the application of performance equation of the plug flow reactor, but it's basically fourth example from your book, chapter number 5. So again, I have told you many times before that whenever you have a problem or numerical, you have to read the statement very carefully, and you have to read it one time, two times, three times, so you know actually basic understanding of the problem, and then extract the data and know what is given, what you have to find out. So same case here, a homogeneous gas reaction A goes to 3R has a reported rate at 215 degrees Celsius. The rate of the reaction is given to is equal to 10 raised power minus 2 Ca power half moles per liter per second. So this is the given chemical rate equation. So find the space time. We have to find the space time tau needed for 80% conversion of the 50% A and 50% inert feed. Like so, in the feed we have 50% A and 50% inert feed to a plug flow reactor operating at 215 degree Celsius and 5 atmospheric pressure. And the concentration is also given. The initial concentration is equal to 0.0625 moles per liter. So here you can see the figure which shows the plug flow reactor. So we have an input and we have output. We have input of 50% A and 50% inert. That means if you have 1 mole per 1 mole per minute the flow rate, so half will be the 50% will be A, zero point 0.5 will be A, zero point 0.5 will be the inert material. So that's the like you have to take care of the what you are entering and leaving in order to calculate the EA, the volume expansion factor. And we need to calculate the time. So here's a mistake. It's not regular time, it's tau for the plug flow reactor. And the conversion is given 0.8. So these are all the things which are given. Now we move to the solution. So class, here you can see that first of all we will calculate the EA value, the volume expansion factor, in order to know that it's a simple case or it's a varying density, it's a constant density or varying density case. If it's constant density, we'll have put EA is equal to 0, otherwise we have to use the EA value. So you know that in the start we have 50% inert and 50% the regular reactant A. So that means if we have two volumes of feed gas, for example, two is the so one will be the inert and one will be the actual reactant. So in like reality, we if you see the chemical reaction, it goes 1A gives you 3R. So the stoichiometric coefficient will be A, and A is 1 and stoichiometric coefficient of R is 3. But you know that we have 50% inert, so one part of inert is also coming in the reactant that will occupy the volume also in the reactor. So we have one part of the reactant A and one part of the inert in the inlet. So we that 1 plus 1 gives you 2, and now the outlet was 3R. So inert will also come out, so 3 plus 1 becomes 4. So we have to also incorporate the inert substance which is entering in the overall calculation of volume expansion factor. So uh, you can see if we put 3 minus 1 over 1, we will get 2. So that will be incorrect. So we have to take the value of inert also. So 4 minus 2 divided by 2 gives you 1. So EA value is 1. So here you can see we have used the performance equation. This is the performance equation of plug flow reactor. Tau is equal to Ca naught, and applying the limit 0 to xaf dxa over minus Ra. So now if we the rate of reaction was given, and we put the rate of reaction and in the terms of conversion, and also Ca naught value was given, xa was given to 80%. So we come up with this expression that is equal to tau is equal to C A naught power 1 by half over K, and integration 0 to zero point 0.8 and 1.1 plus xa over 1 minus xa power half dxa. So we have, this is the function which we need to calculate inside the integration. That's the value we need to solve in order to solve this expression. So first of all, we will there are three different methods to calculate the integration, to solve the integration: graphical method, numerical method, and analytical method. From the three methods we will see which is solved here in your book, and then you can utilize which method is more simpler and more easier, and then you can utilize in the further problems and examples. So here you can see the we have divided the xa value into various small like fractions. From of course conversion from first goes to 0 to 0.2, and then 0.4, 0.6, and then final is was the 0.8. So we have to solve this expression 1 plus xa or 1 minus xa. We put the values of xa, and then we get this value, and when we get the its power to half, we get these values. So these are the five values. If we have 0 xa, we have one value of 1 plus xa or 1 minus xa power half, and then we have 0.2, we have 1.227, and if we have 0.8, we have three value of this function. So these values that are already calculated, you can see in this table. You can also solve by the numerical methods of the different rules. Like we have trapezoidal rule, 2-point rule, we have Simpson's 1/3 rule, 3-point rule, Simpson's 3/8 rule, 4-point, and Simpson's 5-point quadrature rule. So I suggest you can use this. These are the numerical methods by which you can directly put the values in the formula and calculate the value of the function. For example, if we see Simpson's 1/3 rule, it's the second one from the top right side. We solve the function, we will give the apply the limit, and we can directly use this expression age over 3 function of first value, then 4 function of second value, plus function of the third value. X naught, of course, I am taking is the first value, because although it's x0, but it's the first function, second function, third function. So this is only 3 points you can utilize, and just put the values of h and these function values, and you can solve the integration and get your answer. So h, how you calculate h is the x2 minus x naught divided by 2, and how you determine the x1. These x1, x2 are the conversions, like for example 0, 0, 0.2, 0.4, 0.6, 0.8. So you have to take the initial and the last and choose in between. Like for example, you can choose 0, 0.4, and 0.8. So this is 3 points you have chosen: 0, 0.4, 0.8. So in that values you can put those values in the function. Function was what? 1 plus xa over 1 minus xa power half. That was the function, and the answer of the values you will put in this expression, and then you can final solve the function. So this is how you solve the numerical evaluations of the integration by this method. So we will first see the solution from the graphical method. For graphical method, we have to plot the graph between the actual limits which we have applied. That is the conversion in our case, or in the x-axis 0 to 0.8, and the y-axis we will plot the function value, which comes out to be 5 values. The first value was 1, second was 1, 1.227, third was 1.5 something, 58 I think, and third value was 2, and last value was the 3 value. So the how you solve the area, calculate the area, just need to multiply the final value of the x-axis 0.8 and average height, that you can calculate by taking the average of the 5 points. That comes out to be 1.7, and the average height, you just multiply these, and you can get the final answer of the integration solution 1.36. So this is the area under the curve that comes out to be 1.36, and basically this have the uh, solution of the integration that we have solved. So from the graphical method we get the answer of 1.36, and from numerical method I just showed you four different formulas. So we can use the Simpson's 5-point formula, like in Simpson's rule according to even number of uniformly spaced intervals on the x-ray. So this is the Simpson's 5-point formula, and from this you can see just we need to put the values of the functions in the expression and multiply it with the limit 0 0.8, and you get the final answer. So it comes out to be 1.331. So from the graphical method we have the answer of 1.36, and from the numerical method we have the answer of 1.331, and from analytical method you can also do by this relation by solving this integration, and on the right hand side you apply the limit and then 1 plus xa over 1 minus xa square root, and you solve it and you get answer of 1.328, that more close to the numerical integration. So in summary, the method of integration recommended depends on the situation. Method of integration recommended depends upon the situation. In this problem, probably the numerical method is the quickest and simplest and gives a good enough answer for most purpose. So answer is like you just need to use one method, don't need to use all the three methods in the exam or in your solution. You just can use numerical method, or if you like graphical method is also okay. So graphical method or numerical method is quickly used, so you can just put the value here. Now you know that this is the tau is the this is the tau, the relation was Ca naught power 1 by half over k, and the integration just put the value of integration here 1.33, and we get the answer of the space time, that is 33.2 seconds. So this is the space time for this particular problem that we have calculated. I hope you understood this. So let us move towards the next example. So the example statement is the homogeneous gas decomposition of phosphine 4pH3 gives you P4 and 6H2. Proceeds at 649 degrees Celsius with the first order rate minus R. Phosphine gives you 10 per hour. C concentration of phosphine. It is 10 is the value of reaction rate constant. So what is required? We have to find what size of plug flow reactor operating at a temperature of 649 degrees Celsius and 460 kilopascal can produce 80% conversion of the feed consisting of 40 mole of pure phosphine per hour. So here you can see you are given the temperature, pressure, order of the reaction, K value, conversion, molar flow rate, Fa naught 40 moles per hour, molar flow rate. So you have to calculate the volume of the plug flow reactor from this problem. I hope you can do it easily. So here one thing is missing, you are not given with the initial concentration, but you are given the temperature and pressure. So you can utilize the ideal gas law, like PV is equal to nRT, and from there you can rearrange it. N over V is P over RT. So P pressure is given, R universal gas constant, and T is the temperature. So N by V equals to concentration, number of moles per unit volume. So you can calculate the concentration from the ideal gas law. So if we simplify the reaction, let us A equal to pH3, R equal to P4, S equal to H2. The reaction becomes 4A gives you R plus 6S. So reaction rate, the chemical reaction rate is given by this expression, minus R is equal to 10 per hour Ca. So here we don't need to solve the integration. We just use the final expression which is being used here rather than the integration calculation. So final expression is volume of the reactor is equal to Fa naught over Kca naught 1 plus Ea ln 1 over minus 1 ln 1 over 1 minus xa minus ea xa. So you have to now fa naught is given, k is given, ea you have to calculate, xa is given, and ea and ca you have to calculate, and just put the values in this expression and find the volume of the plug flow reactor. So as I explained before, we have been given the concentration, so we can calculate the concentration by the universal gas law, like P over RT. So we put the pressure, convert into pascals, and then convert the temperature into degree Kelvin, and the R value. So we get the concentration that becomes 60 moles per meter cube. This is the like concentration, initial concentration, which was not given, but we calculated from the. So you can see that if you are not given the concentration in any problem, so don't panic, you can find out by the conditions of temperature and pressure. So for another case, EA, you know that we have expression 4A gives you R plus 6S. So in the product we have 6 plus 1 total stoichiometric coefficient, and in the reactant we have 4. So 6 plus 1 means 7. 7 minus 4 over 4 gives you 0.75. So it's a varying density case. EA is not equal to 0, and conversion is 0.8. So you put all these values in that expression, and you get the final answer. So for this conversion 0.8 for the first order reaction, and for this reaction we get the volume of plug flow reactor equals to 148 liters. So in this slide you see that we have table 5.1 from your textbook, and this slide shows you the performance equations of nth order kinetics, and where volume expansion factor is 0. So if you see, we have 3 columns and multiple rows here, and in the first column you are given the order and the k values, like the rate of the reaction. For example, you have n order and minus r is equal to k. Zero order reaction, then n1 first order reaction, and 2 second order reaction, and any n uh, and then you have these are for the irreversible reaction, and then for the reversible reaction also the expression is given and general rate. And then second column you can see is the performance equations for the plug flow or batch reactor. You know that the plug flow and batch reactor have same performance equations for constant density case. EA is equal to 0. So you can see for the plug flow reactor, for zero order reaction, the equation becomes K tau divided by Ca is equal to Ca naught minus Ca over Ca naught is equal to Xa. This expression has been derived, and after the integration have been solved by numerical method, and directly you don't need to do the integration in this case. Directly put the values and calculate the unknown, for example the space time or k value or any unknown which you will be encountering in the problems. And general rate, you can see tau is equal to integration of from Ca to Ca naught dCa over minus Ra, or Ca naught integration 0 to Xa dXa over minus Ra. In the third column you can see we have performance equation for the mixed flow reactor, and same for the zero order, first order, second order, and then any order n, and then you have the reversible reaction. Also you have the expression there. This table represents the performance equations of nth order kinetics, and here the volume expansion factor is not equal to 0. That means that it's for varying density cases. And again we have 3 columns and multiple rows here. In each row you can see the order, zero order for first order, for second order, for any order n, and for first 4 rows represents the uh, irreversible reactions, and the final fifth row represents the expression for the reversible case, reversible reaction. So the performance equations, this is only for the plug flow reactor, because batch reactor uh, is not applicable for the varying density case. So we have plug flow reactor and mixed flow reactor, the performance equation. So here you can see the solved integration expression by numerical methods have been given here of the first order, second order, and uh, first order for the reversible reactions, and also for the mixed flow reactor for the varying density cases. So you can utilize these performance equations for the given case and calculate the unknowns from the known values. Mostly we need to require the space, time, and k value uh, from these expressions. So now we will solve the first 10 problems from the chapter number 5, and here are the statement of first two problems. So again, in the numerical problems you have to read the statement very carefully. I will share the statements and the solution of the first 10 problems in today's lecture. So first of all, we'll go through 5.1, which says that the consider a gas phase reaction 2A gives you R plus 2S with unknown kinetics. So if a space velocity is 1 per minute is needed for 90% conversion of A in a plug flow reactor, find the corresponding space time and mean residence time or holding time of the fluid in the plug flow reactor. So you have to find the space time and mean residence time or holding time in a plug flow reactor. That's the simple. So you are given with a space velocity, that's reciprocal of space time. So space time will be, you can just easily say by reading the statement, the space time will be 1 minute, because one is space velocity, so 1 by 1 is space time. 90% conversion is given, and now we need to calculate the holding time or mean residence time. So second problem is in an isothermal batch reactor, 70%, this is the conversion of the liquid reactant is converted in 13 minutes. So you are given the time and you are given the conversion. This is for the batch reactor. So space time and space velocity are needed to effect this conversion in plug flow reactor and in a mixed flow reactor. So you are given the conditions of batch flow reactor. So if you see that we are given conversion and time, so maybe you have to find out some thing from the performance equation of batch reactor, like the k value or reaction rate constant or reaction rate, anything, and then you can put that into the performance equation of mixed flow reactor or plug flow reactor. So if you understand the problem, that what you have to do, what you are given, then half of the problem is already solved. Let's move forward for the solution. So this slide represents the solution of problem 5.1 and 5.2. You can see that 5.1 we are given the chemical reaction 2A gives you R plus 2S, and then conversion is 0.9, 90%. Space velocity was given in the statement 1 per minute. So space time is 1 by S, reciprocal of the space velocity. So it comes out to be 1 minute. So space time is 1 minute, that's already calculated. Now we calculate the holding time or mean residence time. For that we need to go to the actual reaction conditions. Space time, you can just simply use the formula like 1 over S for space time, but uh, to 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 have the residence time and holding time for the at specific conditions, you have to go through the volumetric expansion factor, and then volumetric flow rates, what will be those, and the conversion. So you have to incorporate all these given things. So first of all, we will calculate EA, that comes out to be stoichiometric coefficient of the product minus stoichiometric coefficient of the reactant divided by the stoichiometric coefficient of the reactant, that comes out to be 0.5, and VF, the final volumetric flow rate, is equal to V naught initial volumetric flow rate 1 plus EA XA, and by this we can develop an expression between Vf and V naught. So if we put those values, EA 0.5 and XA 0.9, and we get the expression Vf is equal to 1.45 V naught. So now we know that holding time is T is equal to V by Vf, and V by Vf is V by Vf is equal to V naught into 1.45. We put these values. Now V by V naught, is 1. That's the space time. V by V naught is 1 is equal to space time, and 1 divided by 1.45 we get the answer. So it's 1 divided by 1.45, we get 0.69 minutes. This is the holding time. So but in the plug flow reactor, since the gas reacts progressively as it passes through the reactor, expands correspondingly, therefore holding time is 1 minute. So in the second problem, you can see we were given the conversion 70%, that's equal to XA is equal to zero point 0.7. Time was given 13 minutes, so it's first order reaction. For first order reaction, we know that minus R is equal to KCA, and minus ln1 minus XA is equal to KT. And this you can develop, already developed. So from here, we have this expression we developed in chapter number 3. You already know that. So here we calculate the K value 0.0926, the reaction rate constant. So for mixed flow reactor, you know that we just have uh, we just have we calculate the space time. That's the its performance equation is equal to tau is equal to Ca naught XA over minus Ra, and when we are given all those values, we can just put this and convert the equation in conversion form, and we put the values of the K and the conversion, and we get this space time that's equal to 25.2 minutes. And for the plug flow reactor, it has the same, you don't need to solve the integration, it has the same space time as that of the batch reactor, which already given 13 minutes. Now in uh, 5.3 and 5.4, you can again read the statement very carefully. 5.3 is a stream of aqueous monomer uh, A 1 mole per liter and 4 liter per minute. So this is given 1 mole per liter is the given the concentration, and 4 liter per minutes are the volumetric flow rate. Enters a 2 liter mixed flow reactor. So in the statement you can see we are given the concentration, volumetric flow rate, and volume, 2 liter volume. Mixed flow reactor is radiated therein and polymerizes as follows. In the exit stream, we have the concentration like Ca is equal to 0.01, and for a particular reaction product, WCW uh, the concentration is 0.0002 mole per liter. So what we have to find? We have to find the rate of the reaction A and the rate of formation of W, the product. And in the problem 5.4, we plan to replace our present mixed flow reactor with one having double the volume. And for example, if you have mixed flow reactor in place of 1 liter, so now you are replacing with it 2 liters volume. For the same aqueous feed, this is the concentration, you name mole per liter is the concentration, Ca naught, and the same feed rate. Find the new conversion, the reaction kinetics are represented by this reaction goes A to R, and minus Ra gives you KCA power half, and present a conversion is 70%. So let's move on to the solution of problem 5.3 and problem 5.4. First, we'll discuss about the solution of 5.3. So here you can see in the top we are given the values of volume, that is 2 liter, volumetric flow rate is 4 liter per minute, initial concentration is 1 mole per liter, and final concentration is 0.01 mole per liter. So it's a chain reaction, and then we are given we can calculate the space time, that is equal to V by V naught, volume over volumetric flow rate. 2 divided by 4 gives you zero point 0.5 minutes, and then you utilize the performance equation of MFR, that is minus RA gives you Ca naught minus Ca divided by space time. It's a simple relation, you just put the values. 1 minus 0.01 or divided by zero point 0.5 gives you 1.98. So the rate of reaction with respect to A is 1.98 moles per liter per minute. Now move on to the next, the rate of reaction with respect to W, where that is a product, and its initial concentration is 0, Cw naught is 0, and Cw is given as 0.0002 moles per liter, very low concentration. So we put these values in this. So this is the product. So if you have put minus sign on the left side, minus Rw, here you can write minus Cw naught plus Cw divided by space time tau. So putting these values, we get the answer is 0.0004 moles per liter per minute. Now move on to the problem 5.4, the solution. Here the rate equation was given, that is equal to minus Ra Kca 1.5, Xa was 0.7, the conversion for initial volume, tau V by V naught, you know that tau is V by V naught, is equal to Xa divided by minus Ra, that's the performance equation for the mixed flow reactor. And if we put the values of minus Ra as given and convert the conversion and write it in conversion form and open the expression, we get Xa multiplied by Cn naught divided by K in multiplied by Cn naught 1.5 power 1.5 multiplied by 1 minus Xa power 1.5. And further we write this in form of K, write the expression in the terms of K, we get this expression. Now put the value of 0.7 Xa that was given already in the statement, conversion 70%. So when we put the 70% conversion, we get this expression K is equal to 4.260 divided by Cn naught power 0.5 multiplied by V naught. So this expression has been developed. Now you know that the expression statement says that we have to double the volume of the new reactor. So we just take the new volume V prime give equal to 2V, that was the previous volume. So again now we have to calculate the conversion, that how much conversion will come with if we increase the volume 2 times. So the new space time is V bar divided by V naught, V prime divided by V naught, and we again open it, or space time is also equal to according to the given conditions performance equation, Vxa multiplied by Cn naught K divided by K into Cn naught power 1.5 into 1 minus Xa 1.5, that's the conditions given. So if we solve this expression, we end up with uh, uh, in place of V bar we put 2V, and simultaneously solve this expression of K derived earlier, and this expression we come up with this expression 8.52 Xa divided by 1.1 minus Xa power 1.5. Now we take scale both sides and make an numerical equation, so we can solve it numerically. This equation 72.6 minus 72.6 Xa cube plus 216 Xa square minus 217 Xa is equal to 0. So while fitting the values, we find out that Xa at 0.79 satisfies this expression. So you see that by doubling the volume, we have increased the conversion of around 10%. That was initially 0.7, 70%. Now we are near to 80%. Now let's move to the problem number 5.5 and 5.6. So again, let's read the statement first. 5.5 statements tells us about an aqueous feed of A and B, 400 liter per minute is the volumetric flow rate, and 100 millimoles of A per liter, that's the concentration, and 200 millimoles B per liter, that's the concentration of B, is to be converted to product in a plug flow reactor. The kinetics of the reaction is represented by A plus B gives you R, and the rate equation is given as minus Ra 200 times Ca into Cb. So find the volume of reactor needed for 99.9 conversion of A to the product. So it's a typical numerical involving the performance equation of plug flow reactor. So in the short time we will see the solution. So for the problem 5.6, a plug flow reactor 2 meter cube, that's the volume, processes an aqueous feed 100 liters per minute, that's the volumetric flow rate, containing reactant A. Concentration is Ca naught 100 millimole per liter. This reaction is reversible, so it's like moving forward and backward, and is represented by the chemical reaction shown below. A goes to R and then R goes back to A, and the rate of the reaction is given 0.04 Ca minus 0.01 Cr. So please first find the equilibrium conversion XAE, and then find the actual conversion of reactor of A in the reactor. So these are the statements. That now let's move towards the solution. So let us see the solution of problem 5.5. The solution of problem 5.5, here you can see that the chemical reaction given A plus B gives you R, then rate of the reaction given as in the form of rate equation 200 times Ca times Cb, all these expressions. Now Ca naught was 100 and Cb naught was 200, volumetric flow rate was 400 liters per minute, and Xa was 0.999. So you know that in the previous slides we have discussed the two tables, table 5.1 and 5.2. The 5.1 table shows the performance equation of batch, plug flow reactor and mixed flow reactor for different orders, starting from 0 order to first order, second order, nth order, and for the reversible reaction. And here we have developed final expression that you can utilize directly without solving the integration uh, form. So this is the expression right for the second order. In that table you can see K tau multiplied by Ca naught multiplied by m minus 1 is equal to ln m minus xa m into 1 minus xa. So we need to calculate the volume. So here m is 2, so substituting all the values, and in this expression, and second equation, the space time V by V naught, we get this expression from the performance equation, and we end up with 0.31. So 0.31 into 400 volumetric flow rate, we calculate the final volume, that's 124 liters. So in the second problem of this slide 5.6, the solution, here you can see we have reversible reaction and rate of reaction is given, and K1, K2 is can be seen from the rate expression, and M is given, so their concentration is same, so it's low. And K1, in fact Cr naught is 0, that's in the start, so the ratio is 0. The K1 by K2 is we have this expression, the equilibrium constant. From here we can see that the XAE is 0.8, like equilibrium concentration will be 80%. So we know K1, K2, and we have calculated XAE. Now for the first order plug flow reactor reversible expression, we can use the performance equation for plug flow reactor and solve the integration. We you know that the space time is equal to Ca naught Ca naught into integration dxa or minus Ra is the performance equation for plug flow reactor. So minus Ra is equal to this expression 0.04 Ca naught 1 minus Xa minus 0.01 Ca naught m plus Xa. So we have converted the expression in terms of conversion. So by integrating the terms we get we get this expression, and final expression we get K1 multiplied by V naught into m plus 1 divided by m plus XAE, and substituting all the values for, like this equation we have developed, all the values we end up with is minus ln 1 minus XA by XAE is equal to 0.64. So XAE we already calculated before, the ratio becomes 0.68, and then we multiply with this by XAE. So the final conversion will be 0.38. So the conversion for the given conditions is calculated as 38%. Now let's move to the next problems, that's problem 5.7 and 5.8. The 5.7 problems, we read the statement. The off gas from a boiling water nuclear power reactors contains a whole variety of radioactive trash. One of the most troublesome being Xe 133 half-life is 5.2 days. This off gas flows continuously through a large hold-up tank in which its mean residence time is 30 days and where we can assume that the contents are well mixed. Find the fraction of activity removed in the tank. So this statement looks a typical practical problem. So, but of course we will utilize the things given in that problem. We use the concept of the things we have studied and try to solve it. And for the next problem, problem 5.8, the statement shows that a mixed flow reactor 2 meter cube, that's the volume given, processes an aqueous feed 100 liters per minute, that's volumetric flow rate, and containing reaction A, CA0 gives you the concentration, hundreds millimoles per liter. The reaction is reversible and is represented by this chemical reaction. A goes to R and then reverse R goes to A, and the rate equation is given as minus RA is equal to 0.04 CA minus 0.01 CR. So the values of K1 and K2 are given. What is the equilibrium conversion XAE and the actual conversion in the reactor? This problem looks similar to the problem 5.6, and I hope you can understand it better. Now let us move towards the solution of problem 5.7 and problem 5.8. So you know that we were given half time for this reaction. Tau gives you one half is 5.2 days, and mean residence time was given 30 days. So K value is equal to 0.693 divided by half-life. That's the expression from the book, and we get this K value the reaction rate constant. Now for a mixed flow reactor we know that Ca by Ca naught is equal to 1 plus 1 divided by 1 plus K tau. So calculate the if we calculate Ca, the ratio of final concentration to initial concentration, it comes out to be 0.2. So we have tau was given, and we calculated the K value from that using the half-life method, and it's the ratio between the two concentration, initial concentration, final concentration, comes out to be 0.2. So we just need to calculate the conversion fraction of the activity. XA, XA is equal to 1 minus CA over CA naught, and we put values of CA by CA naught 0.2, and we get 0.8 the answer. So 80% is the conversion. Now move towards the problem 5.8. It's similar to problem 5.6. So we have the reversible reaction, and the rate equation is given. Now K1 is 0.04, K2 is 0.01, and the ratio of the final product, our initial concentration of the product divided by the, that Cr naught in the start is 0, so M will be 0. So K1 divided by K2 is equal to XAE divided by 1 minus XAE. From here we calculate XAE is 80%. So X is 80%. Now we need to calculate this is the equilibrium conversion. Now we need to calculate the actual conversion. So first order mixed flow reactor, for the reversible reaction, we have this expression V by V naught this is the performance equation for the mixed flow reactor, and for the reversible reaction we put the value of rate of the reaction, and we put the initial concentrations, and we calculate substituting all the values in that, and we end up with this expression. XA is equal to 0.8 minus 0.8 XA minus 0.01 XA. So we have developed an expression, we solve it, and we get the value of XA that comes out to be 0.4. So the 40% will be the conversion in this case. So let us move towards the last two problems of this today's session. problem 5.9 and problem 5.10. So first of all, you read the statement very carefully of problem 5.9 is a specific enzyme acts as a catalyst in the fermentation of a reactant A at a given enzyme concentration in the aqueous feed stream. Find the volume of plug flow reactor. So you know that in all the problems we have either batch reactor or mixed flow reactor or plug flow reactor. So here again we have plug flow reactor. So the conversion is given 95% and concentration given is 2 moles per liter. Volumetric flow rate is given 25 liters per minute, and the kinetics of the fermentation at this enzyme concentration is given by this reaction. So we are given what we are given. We have a plug flow reactor case. We have a chemical reaction given. We have volumetric flow rate given. We have volume. Uh, we have to find the volume in the end. Conversion is given and concentration is given, initial concentration. So utilize the performance equation of plug flow reactor. So in the last problem of today's session 5.10, if you read the statement, a gaseous feed of pure A 2 moles per liter. 2 moles per liter means is the concentration, and 100 moles per minute, that's the volumetric flow rate V naught, decomposes to give a variety of products in a plug flow reactor. And the kinetics of the conversion is represented by A gives you 2.5 products. So here don't panic. 2.5 means the stoichiometric coefficient product could be any R or S or any products, multiple products, because S has been come in the end, so there will be multiple products. So overall the rate expression is given. First order is, you know, so 10, that's the reaction rate constant value, and Ca is the concentration. So find the expected conversion. You need to find the conversion XA in a 22 liter reactor. So what we are given? We are given the concentration Ca naught, volumetric flow rate, reaction kinetics, the rate equation, the volume, and we need to calculate the conversion. So let us move towards the solution of problem 5.9 and problem 5.10. So first of all, problem 5.9, you know that we are given the chemical reaction A goes to R in the presence of enzyme. It's a biochemical reaction, and the rate equation was given as minus R is equal to 0.1 Ca by 1 plus 0.5 Ca. So volumetric flow rate was 25 liters per minute, initial concentration was 2 moles per liter, and conversion was 0.95 or 95%. So we have to calculate the volume for this case of the reactor, plug flow reactor. So now we see that the performance equation of plug flow reactor V by V naught, the space time is equal to dCA over minus RA, starting from initial concentration to final concentration. So we substitute the value of minus RA in this expression, and putting the values and solving the integration, we end up with this expression. And these expressions you can utilize directly from the table 5.2 also. And for this case we have come out with V by V naught is equal to 39.45 to answer, and we calculate the V by just multiplying it by the volumetric flow rate 25. So it comes out volume to be 986 liters. So let's see the solution of problem 5.10. So we are given the chemical reaction A goes to 2.5 products, and the rate equation is minus RA 10 Ca. Plug flow reactor, volumetric flow rate is given, Ca naught initial concentration is given, volume is 22 liters. So from the stoichiometry, it's a varying density case. Ea is equal to 2.5 minus 1 divided by 1, that's it comes out to be 1.5. So we just use the expression from the table 5.2, where is the varying density case, and we use the performance equation of plug flow reactor. V by V naught into Ca naught gives you integration 0 to x xaf dxa minus Ra. So we open this, we get Ca is equal to Ca naught 1 minus xa over 1 plus Ea xa. This is the in fact comparison of Ca and xa. We insert this value here and we end up with this expression. So solve it simultaneously, and we end up with this form. 4.4 gives you 2 minus 2.5 ln 1 minus xa minus 1.5 xa. So solve this numerically, we get the answer of 73%. The conversion that is 0.77733, and it comes out to be 73.3 conversion in this case. So we come to the end of today's lecture. Thank you very much for listening, and I hope that the solutions will be understood better. In any case, you have any questions, you don't understand any point, you can just contact me through email or WhatsApp, or just message to your class representative about the slides, and then also we can discuss this in the as the physical classes will resume. Thank you very much.